Hi everyone, we are Group 2. Our project topic is mitigating bias in GPT-2. Now it's my turn to introduce the first part. The main goal of our experiment is to explore the biasing method for the GPT-2 language model. I will start by introducing the background. As we know, bias in large language models mainly comes from stereotypes in the data training, and it manifests at two specific levels, the data level and the structure level. Our goal is to use the method in these two papers to try to reduce bias of GPT-2. Next, let's move into the core idea of FASB algorithm. We know in the transformer architecture, different attention hams play different roles, especially their contributions to model performance and bias application are not the same. Based on this, our aim is very clear. We need to identify and remove the hams that amplify bias, while strictly preserving the hams that are critical for maintaining the model's language capabilities. A key property of this algorithm is that it's a training-free method. It means we don't need expensive fine-tuning. Instead, we directly prune the model structure, which greatly improves efficiency. In the process of experiment, we evaluated all attention hands of GPT-2 individually. We calculated the PPL impact value and the bias impact value for each hand, as shown in the formula on the slide. These are calculated as the difference between the value after pruning and the value before pruning. A high PPL impact means the hand is critical for capability, while a high bias impact means the hand is highly toxic. Our strategy has two steps. First, we lock the top 30% with the highest PPL impacts to ensure the baseline performance is protected. From the remaining unprotected hands, we select the top 10% with the highest bias impact for removal. Now let's look at the result and analysis. First, we can see visual bias safely decreased by 70%, proving the method is effective in this dimension. However, the cost was significant. The method PPL increased by 23%, which indicates a noticeable loss in language generation performance. We can see that gender bias appears to increase by 104%. Upon analysis, we think this is due to an indicate failure. The baseline scores for gender bias in the original model was extremely low, mathematically almost zero. In this case, anytime the rhythm fluctuation may make a huge percentage change. In summary, while FAST is effective for vision debiasing, it comes with a significant performance trade-off, sacrificing too much model capabilities for the sake of failures.
Hello everyone, I reproduced and analyzed the Schema-10, a simple tool to reduce social biases in models like GPT-2. Its core idea comes from cognitive dissonance theory. We add optimized noise to group words like he or she and black or white in the model's embedding layer to break fixed stereotypes. The framework uses Bayesian optimization to find the best noise, then fine-tunes the model lightly. For reproduction, we use group words like gender, race, occupation, religions, and trait words from the ABC framework. We measure bias with stereosize SS score and IC80 score and performance with perplexity on Wikitext2. Our results here. Overall SS score drop, racial bias fails, IC80 score rose, and perplexity only increased 22.1% within a controllable range. Schema-10 needs little data and no labeled bias state. It's lightweight and works great for low-resource scenarios, effectively reducing multi-dimensional biases.
Now I'll introduce our hybrid method. Our approach combines two ideas, scheme-tune and FAST. Scheme-tune adjusts the embedding space to weaken stereotypes, while FAST removes attention heights that strongly amplify bias. The hybrid first fixes the representations and then cleans the structural pathways where bias is propagated in the transformer. Based on the analysis, hybrid prunes 40 heads, which is about 10% of all heads. These were the heads that carried the strongest bias signals, so removing them significantly reduces structural bias while keeping performance relatively stable. In terms of results, hybrid works especially well on gender bias, reducing it by 58.65%. However, for race bias, the model shows an increase. This suggests that small models like GPT-2 have limited capacity, and improving one type of bells may unintentionally worsen another. Overall, our work shows that debugging can be lightweight and interpretable. By reproducing SCM-tune and FAST, we found that bells follow two paths inside transformers, semantic injection and structural application. Hybrid addresses both levels and achieves strong improvements with minimal pruning. For future work, we plan to extend SCM-tune to race-related schemas, design multi-bells, a well pruning strategy.